Exploring opportunities for early adopters with COROB's multi-robot cells summarizes exactly what we are here to do. COROB has developed cooperative multi-robot solutions for arc welding-based manufacturing, and we want to bring them into real industrial environments. To do this, we are reaching out to potential end users and early adopters like you. The idea is simple. After this workshop, we invite you to submit your own manufacturing scenario for our consideration. Applications will be reviewed, and selected demonstration cases will be implemented directly on the COROB's multi-robot cells. This is a concrete opportunity to test cutting-edge cooperative robotic technology in your industrial context, and important, with no development cost for you. In this session, we will guide you through the project, its technological pillars, and in particular, we will explain the use cases that we have been developing through the last years. By the end, you will have a clear idea of what COROB can do and whether your scenario might be a good fit. Let's get started. Okay, so starting with providing some context about the project, COROB is a Horizon Europe project that started on the 1st of October of 2023 and has been running through the last 3 years and will be finishing of September of this year. The project focuses on 3 core themes that will be cooperative robotics, human-centered manufacturing, and platform-based integration. By the end of this session, you will have a clear understanding of why these themes are central to this project. At its core, COROB aims to address these challenges, or the challenges of modern flexible manufacturing, by integrating multiple robots, artificial intelligence, and human expertise into a single and cohesive solution. Okay, so what's COROB? As mentioned, COROB is a flexible, cooperative, and intelligent multi-robot system specifically designed for arc-based manufacturing processes, but this is important, easily scalable to other processes. The system responds to one of the biggest challenges in today's industry, that will be the high-mix, low-volume production, where manufacturers must produce many different part variants in small bunches, quickly and with high quality. To achieve this, COROB delivers the following 4K capabilities. The first one will be the multi-robot cooperation for complex tasks, such as jigless welding or large-scale component repairs. Second, fast and flexible reconfiguration, enabling adaptation to different product variants, even down to single unit bunches. Third, human-in-the-loop AI, combining operator know-how with advanced automation. And finally, a sustainable approach that reduces process time, energy consumption, and material waste. The COROB solution rests on 3 fundamental technology pillars that will be, first of all, robotics, artificial intelligence, AI, and data and interoperability. The first one, robotics, we design a multi-robot cell layouts optimized for reachability, stiffness, dexterity, and collision avoidance. We have developed hardware and software that enable synchronized or semi-coordinated motion across robots from different vendors, which is nowadays highly relevant in real industrial environments because machines for different brands already coexist. The second pillar is artificial intelligence. We apply AI for real-time quality assessment, process optimization, and adaptive control. We have built a dedicated tool that allows non-expert operators to train, manage, and deploy AI models. And we also combine active learning with reinforcement learning to integrate operator knowledge and adapt to changing conditions. The third pillar is data and interoperability. We use a modular middleware based on Asset Administration Cell, AAS, uh, enabling plug-and-play integration of robots, sensor, or, or any software. This creates a unified data layer that makes it straightforward to add new AI tools, sensor, or any other robotic device without any custom integration work. What would be the ambition of the COROB project? The central goal of COROB, maybe I am repeating myself a little bit, but to make it absolutely clear, is to develop a flexible, cooperative, and intelligent multi-robot solution, not only for the use cases that we will but important to a scalable other processes. The idea is to position COROB as a comprehensive solution, extending beyond the specific use cases addressed in the project. The system relies on a cooperative robotic assembly supported by inspection, monitoring, control, and AI technologies, with the objective of optimizing welding operations and the surrounding manufacturing stages in terms of time, cost, energy consumption, and resource efficiency. The solution is also designed to be scalable and adaptable to other manufacturing processes as required. And finally, to validate the proposed approach, the project focuses on two semi-industrial use cases that will be introduced shortly. COROB aims to generate impact across three dimensions. On the scientific side, we are developing and integrating novel technologies that combine robotics, AI, and data to boost manufacturing in strategic sectors. We will demonstrate a feasible solution for flexible, agile, and reconfigurable manufacturing using cooperative robots enabled by AI, representing that we consider the next generation of industrial robotics. On the environmental impact side, we proposed rapid adaptation to changing conditions, as I was saying, on the environmental side, we propose rapid adaptation to changing conditions, enabling, on one hand, a significant reduction in fixtures and scrap rates, and on the other, repair as alternative to new manufacturing. And finally, on the industrial side, the development and adoption of COROB's digital solutions, along with the training materials we are producing, will contribute to restoring European industry digital leadership across the supply chain. Okay, so I will present briefly the both use cases that we have been developing through the last years, starting with the use case one. Use case one centered on a cooperative multi-robot system for flexible manufacturing. The welding process is carried out using a jigless approach, meaning robotic welding without traditional fixtures or jigs, where two manipulator robots hold and present both work pieces to a dedicated welding robot. This eliminates the need for expensive and rigid positioning tooling. In terms of the use case two, deploys a multi-robot cooperative cell for tooling repair using one. The main robot, equipped with a wire arc welding head as an effector, handles the repair task, and together with a 2 degrees of freedom rotatory table, it forms an 8 degrees of freedom processing system capable of repairing very complex geometries. Also, a smaller auxiliary robot is also integrated into the cell for secondary processing tasks, for example, incorporating 3D scanning technologies. Firstly, following, I will explain the main challenges and an overview of the first use case more in detail, and then my colleague Christos will guide you through the second use case. Okay, So starting with the use case one, the jigless welding pilot, it is a vendor-agnostic flexible multi-robot welding cell composed by two manipulator robots for workpiece manipulation and a welding robot The software developed is based on ROS2 framework. That's why we say it is a vendor agnostic and flexible cell, because we can use different robot brands cooperating with each other, and we can adapt or change any robot or cell actuator with a minimum effort. With this, we face the challenge that we previously mentioned. That will be that current real industrial environments machines from different brands already coexist. Second, we implemented vision-based algorithms in this case using a profilometer to correct the workpiece's position and the alignment before welding. That's because the robot precision, the tolerances of the system, the differences between the digital twin we have and the real cell don't have the required precision to do such a positioning, because we are talking about a sub-millimeter gap control between the workpieces. In this case, at this moment, we are welding with a 0.7, 0.8 millimeters gap between the workpieces. We also implemented AI-driven algorithms to correct in real time during the welding the path that the robots are following. This is because the high energy and the heat provided to the workpieces from the welding arc, the workpieces can be deformed and moved, as you can see in the image on the right side. And to don't let the gap open, we correct the robot's position in real time depending on the force and torque measured on the robot flank. We train an AI model using a reinforcement learning model to correlate this measured force and torque with a robot path correction. And finally, we also integrated into the cell architecture some quality assessment solutions just to measure the welding quality during and after the process. And we will go more in detail into them when we see the architecture itself. Okay, here we can see the multi-robot cell we are using currently. We have two ABB robots with different payloads for manipulation purposes, and a Doosan cobot as the welding robot. This demonstrates, or it's important to say, that we are using different brands robots synchronized and cooperating in a single process. This will be the architecture of the cell. We can see that the platform is the central point of the solution. That's why we say at the beginning that is a platform-based integration, because the different solutions are connected with each other through the platform. On the upper side, we can see the different solutions, such as the HMI, virtual reality simulation, digital passport generation for after welding pieces tracking, and the quality assurance systems. For example, starting with the face solution, it corresponds to a high-speed camera around 5,000 FPS measurement that measures the weld pull in real time, and with an AI-driven algorithm can detect and classify the different defects that are happening during the welding. On another hand, we have the sign weld solution. This will do the same as the face solution. It will detect and classify the defects during the welding, but in this case, analyzing the spectrum of the welding light using a spectrometer. Specto is a 3D scanning solution for after welding cut generation and compares the reference cut that the operators input in the HMI with the final welded workpiece. And finally, as the quality assurance system, we will have the SkyBlue MT solution, that is a profilometer-based solution which can give different parameters of the welding bed. For example, the penetration that has had the welding and some more specific parameters. Going through the cell control, as mentioned, we use a ROS2-based software running on a super micro PC, where we control all the actuators on the cell, and then we upload all the data obtained to the platform. And finally, we will have the picking solution, which you will see more in detail in a video later, connected to the trajectory manager software that generates a nominal path based on robotic software. Okay, following, I will explain the workflow that the use case one follows with 5 sequential steps. The first step will be that the operator requests a recipe production from the HMI. At this point, the parts or assembly to be welded are selected. Following, in step 2, the system generates nominal robot paths using the picking solution output, which locates the workpieces in a box through computer vision. The third step will be that the robots will pick the workpieces from the box, align them in the welding position, and the previously mentioned alignment algorithm will correct the alignment and the gap before welding. Step 4, the welding process is executed, as said, with a real-time path correction active throughout. And finally, as the final step, the quality assurance system analyzes the results, generates the digital product passport, and provides feedback to improve future processes. Okay, here we have a small video with the workflow that we are following right now. Here it is the multi-robot cell that we are using with the 2 ABB robots at the Doosan. We have a gripper with two different joints, one for gripping purposes and the other one with an electroimant. The picking solution with the camera mentioned and the workpieces in the box. The camera will detect the workpieces selected and will tell the robot where it is and how it has to pick it. Here the robot will put the workpieces presented on the welding position, and the welding robot, the Doosan in this case, will pass the profilometer to align both workpieces and adjust the gap before the welding. And after the workpieces are welded, they are carried to the quality assessment systems, in this case, the 3D scanning solution inspector. And finally, a brief video of the virtual reality simulation where the operator can see what's happening inside the cell in real time. Okay, so beyond the internal demonstrator shown, COROB opens the door to external use cases, industrial welding scenarios brought by companies interested in exploring this technology with us. The goal is to explore different industrial welding scenarios in high-mix, low-volume production environments. We want to demonstrate how jigless welding technology integrated within a flexible multi-robot cell enables faster changeovers, greater adaptability, and reduces fixture dependency. The 3K focus areas for these external cases will be the first one, reduced setup and changeover times through fixture-free operation, increase manufacturing flexibility to handle multiple product variants efficiently, and finally, improve productivity and resource utilization with coordinated multi-robot automation. If any of your organization has a relevant welding case that could fit this technology, this workshop is the right moment to explore collaboration opportunities. For the external use cases The scenario or the demonstration scenario follows also three stages. The first one will be the evaluation of the requesting manufacturing process. We analyze the part geometry, welding requirements, and technical feasibility within the COROB cell. The second stage is the preparation of the nominal robot parts for the welding of the requesting work pieces. This includes programming the coordinating movements of the three robots and configuring the welding parameters. And finally, as the third stage, the manufacturing, it will be the manufacturing testing and results evaluation with the feedback from the quality assurance systems. Finally, let me walk through the key performance indicators that guide the validation of use case one. In terms of productivity, we aim to reduce fixture cost by 15%, starting from a baseline where tooling represents approximately 40% of the total robotic cell cost. We also target a 50% reduction in part change over time, including fixtures, parameter, consumables, and logistics. On quality, the objective is to reduce machine learning models training effort by quality assurance by 30% while maintaining the same performance level. The current defect rate with existing machine learning models is around 1%. For service, we want to digitalize expert knowledge through active learning so that AI-generated process parameters increasingly require less human corrective intervention. We also aim for an inexperienced operator to complete the full workflow in less time than the current expert baseline. And finally, on sustainability, the target is a 15% reduction in material consumption by replacing multiple fixtures with a single gripper and reducing the scrap ratio to below 1%. Okay, this will be all from my side. Thank you very much for your attention. If you have any question to ask, I will happily answer them. If not, if there is not questions at this point, I will pass the floor to Christos to introduce use case 2.
So, good morning as well from my side. We'll present you similarly to Unai the aspects of one use case and the potentials for collaboration on evaluating external use case in this aspect. So similarly, our architecture is platform-based. So what this means is that on the lower side, we have the operational technology, we have the robots, the 3D scannings, and the whole equipment. And we communicate with either software-related or hardware and software-related sensing solutions, as an example, through the COROB developed platform. We have been supplied through the COROB open call external solution related to the user interface, VR and AR solution, the digital product passport, a layer height control system in order to fix in terms of irregularities a layer control that can be monitored within the process, an additional process monitoring system that is based on multisensorial data, and the preheating solution in order to minimize interlayer cracking when we start the process. So regarding the hardware, we have a main Yaskawa robot with a rotary table that altogether provide 8 degrees of freedom, a Lincoln Electric one welding machine, and a collaborative robot as we discussed before, as well as an industrial PC where we host all different services and software that I will present you later on. That's based on Windows. This is a picture of the cell. You may see here the main robot, which is responsible for the one deposition, the rotary table that provides us 2 additional degrees of freedom, the Lincoln Electric machine, and the collaborative robot infrastructure that it is based as well in a movable base in order to provide us some flexibility. The cobot that you see is responsible for conducting the 3D scanning operation, the defect localization on the part to be repaired, as well as the preheating operations. So how the whole process starts. What we call pre-process is actually when we have received the part and we have mounted the rotary table and we now try to do the repair operation. The first step is identifying where a defect area is. We do that digitally. I will present you later in the demo video how this is conducted, how we tackle this. Then we follow an automated loop for 3D scanning, for scanning and acquiring the repaired area that subsequently will lead us to the reverse engineering, so generate and extract information about the missing material and what needs to be deposited. And following this up, as soon as we have the volume that we need to add to the part, we guide the user through an intuitive selection of the process parameters and more or less the process planning procedure. This intuitive process planning procedure is a bit complex, but it is related in this slide. So as you can see, the user can select the slicing algorithm that is either planar, what conventionally we can see in typical FDM printers and other metal deposition printers. We also have non-planar slicing capabilities and cladding capabilities. As soon as we select the slicing algorithm, we have an AI-based process model that can calculate the bit dimensions, which subsequently handles the slicing automatically. As for selecting the process parameters, we also have an AI-based multi-objective optimization tool that can iterate among the suitable process parameter lists to compensate on quality aspects, sustainability, and cost aspects. So as soon as we have the final plan, we proceed with the G-code generation, and then we post-process the robot program and we visually commission it in Robotic. We also have different process monitoring capabilities in the cell during the process, so we can measure the multiple dimensions, we can measure the cooling rate in order to estimate the interrail cooling time and not have a fixed time. To do this, satellite, porosity, sagging, and spatter among those. Some of those are analytic models and others are based on AI. We can see more details in this video. So as you can see, this is the user interface where the operator does first an initial check of list, and now they want to localize where the defect is. And actually, this is handled by using an edge finder and a Cobalt collaborative mode. So we can just pinpoint where the defect is. You can see those red points that are generated in the user interfaces. And as long as we have the set of the defects, a mesh plane is generated. We use this mesh generated in order to generate the 3D scanning trajectories. So we can select the parameters like patch overlap, distance, etc. These are mostly prefixed because you need to be in standard position for the scanning. And as you can see, the paths are simply like this generated. And then the program to calculate these trajectories and execute this is tested. It's simulated to see if the whole path is reachable. Now you can see that we can open the software for the scanning. This is a commercial software, and we do the 3D scanning. We send the part and the mesh file, and we are finished. As long as we have this mesh file, it is loaded. We see here the theoretical part, and we roughly position it in where it needs to be in order to do an analytic compare of the missing volume. Here you can see the results for the deviation as an example. And subsequently through this procedure, we generated the missing volume. This is actually the missing volume that we need to do. And then as long as we have the missing volume, we can go to the slicing procedure. This is just a demonstrator of the planar, the non-planar slices. It's not an indicative added manufacturing part, but just to give you an idea of the capabilities of the tool that we have deployed. We can either select manually the parameters, we can either select it automatically. Yes, nothing, we do not have the time to analyze this a lot, but as of this user interface that is presented here is related to the multi-objective optimization. We have some initial inputs regarding to the initial height we estimate, and based on it, we can have an analysis and the optimization. A bit on the one process. Here you can see from the platform the different data that we can acquire. On the right side, you see the thermal monitoring data from the thermal camera we have. The cooling time control bits, it's an IO and some flags to say that the cooling time is on. And on the left side, we can see the different one parameters and the parameters from the green well twin process monitoring solution. And this is an example of the layer height procedure we have deployed. We acquire the data from a radar-based sensing solution through the COROB platform. We measure different points across a part that are estimated, that are generated, let's say, by automatically through the post-processor. So we put at, let's say, X layers some points to measure. We compare those with the initial target we have, and we target the robot to do a deviation in order to mitigate these issues. And at last, we can see the digital product passport that can be generated. This is as well an external solution. This is the user interface of the digital product passport. It typically queries all the data from the process using the start and the end time for the job that has been conducted. And we can see different data regarding the life cycle, quality reports that are subsequently follow the product, and an NFT generation of the part. At last, we have as well a small pitch of how the virtual reality solution works inside the robot cell. We can see the robots, we can see the different camera feeds, some relative process parameter data, and just to give a view, a more intuitive view for process monitoring, as well as, let's say, guiding new people in how the cell works. It's a very nice solution. And that's all on my end for the use case demonstration. So I will go about what we target and where we open the door for external use cases. So as part of our project, we can select one or even more application scenarios to tackle repair scenarios regarding different kinds of geometries and challenges. Our main focus is on the toolmaking industry, but of course other use cases are more than welcome, and the material focus is on steels. But in the case you have a very special need, we can be happy to discuss to see if we could tackle that. The scenario would be that we will typically do what you saw in the video. We will acquire the part, we will mount it, we will 3D scan it digitally, prepare the optimized process plan, generate the paths, and manufacture it. And the part will be accompanied by a digital product passport, as well as all the data generated from our monitoring systems. In terms of targets, very briefly, what we target is a 15% reduction in tooling costs. So in comparison with the new, to extend its lifetime by, but of course up to discussion depending on the use case, by 50%, while reducing 50% the resources consumption. We target a 50% reduction in the reconfiguration time regarding to how this could be conducted at the as states. Similarly, a 10% reduction in the maintenance downtime, which is a kind of turnaround time from the tool breakage to a new tool installation. How we do this. Regarding quality, these are user specifics, but we try to maintain as much as possible the quality with the original part. Of course, it is a repair product. And we have other KPIs that we will measure as well, which are related to the workflow itself. So how much time it takes using the conventional method to repair this tool, and how much time it takes with an inexperienced user to guide through the workflow and see if it is more easy to integrate those technologies in the industry. And that's all as well from my side. I would like to thank you for your attention, and please let me know in the case of any questions. I will be more than happy to answer those. I suppose we don't have any questions. So Unai, Flavia, I'm back to you.
Yeah, I think we can close, and the recording will be available on the website. Thank you, everyone.